should eventually tell her so that she doesn't stand here and not sit over her house.
I can give you like a 90% assurance.
What?
I can give you like a 90% assurance.
Really?
Almost I like break my ankle.
So how are we doing?
Tired.
Tired?
Hungry.
I'm probably gonna break my ankle tonight. You can slam it into a wall.
Can you at least tell me if you're gonna break your ankle though, so I can still like kick the boss or something?
90% assurance tonight, yeah. I thought it was great.
We'll take a bus and put them back together.
The bus is 10:40. So.
About what? How much is the bar?
Like $10.
Is it? $8?
$8.25 for like still more than
We are going to be talking about the brain today. When we finish the brain, which will be next Monday, once we finish the brain, then we'll have an exam. That exam will happen next Wednesday. Okay, so it'll be a week from today. That'll be background of psychology, research, and brain. Those will be the three areas covered on the exam. It will be 50 multiple choice questions. Yes?
Can we use some notes on the exam?
No.
No. Okay. Good idea.
Can't use them.
It's gonna be multiple choice.
Multiple choice, 50 multiple choice questions. And if you've been following along and understand what we've been doing, you should be in good shape.
So it'll be on the introduction and chapters 1 and 2. 6.
Yeah, the introduction, like where psychology came from, you know.
Is it chapters 1 through 3 or introduction 1 and 2?
It's chapter 1 and 2, basically. I broke chapter 1 up into 2 parts.
Oh, right, okay.
Okay? Now, on Monday, if we finish all of this material, I may start the next section, which is development, but the first part of development, we're going to look at brain development. Even if we cover brain development on Monday or any part of it, it will not be on the exam. Brain development, we'll look at some other stuff. That's actually in the chapter on development itself. So, okay, but that is where we are. Okay, so everybody knows. I'm sending around the sign-in sheet, so please make sure you sign it before the end of today. We said last time, where we left off, let me just mention where we left off. We were talking about, I mentioned at the very end of class, the central nervous system, then the peripheral nervous system, then I mentioned the autonomic nervous system as one part of the peripheral nervous system. And remember, autonomic means automatic. Right? The two parts of the autonomic nervous system. And we mentioned the autonomic nervous system now because it's here in this chapter, but it will come up again. Right? It will appear again in other parts of the course, things that we look at, because it is involved in, right? The autonomic nervous system does get involved in other things as well that people need. So, just something we need to look at. Again. What we are going to do today is look at some of these parts of the brain, and we will get to cover quite a bit of material today. But the first thing that we said we were going to look at was the brain stem. This is the brain stem right here. Said it's literally the top of the spinal cord. It's where the spinal cord connects to the brain. And we're going to identify some parts of the brain stem, 3 in particular. Parts of the brain stem, components of the brain stem, talk a little bit about what they do. But here in this model, right, this is the brain stem right here. Right, the spine comes up, this is the brain stem. Generally speaking, what role does the brain stem play in general?
It controls the medulla and the cerebellum.
Well, the medulla is part of the brain stem. Generally speaking, the brain stem plays an important role in keeping us alive because it's involved with lots of vital functions in the body. Right? Generally speaking, things that occur outside conscious control that keep us alive biologically. So, when we look at one part of the brain stem right here, this part right here, that's the medulla. That's the medulla. Tell me what the medulla does. Yes? Go ahead.
Connects the brain and the spinal cord.
It serves as a connection between the brain and the spinal cord, helps to facilitate transmission of information, but the medulla does something else. All right, I know the textbook, I think the textbook says heart rate. It's more heartbeat. Right? Medulla controls the beating of the heart. Okay, heart rate is actually, right, there's another mechanism in the brain involved here. But medulla is more heartbeat. Right? What else besides heartbeat? Something else that's really important. Breathing. Right? Heartbeat, breathing. Right? Two very important things controlled by the medulla. As well as your reflexes for things like vomiting, coughing, sneezing, swallowing, medulla function. Okay, that's medulla. Something else, part of the brain stem here, or encased within the brain stem, is this structure right here. And that structure, right, that structure is known as the reticular formation.
The book actually says that that's the thing involved with breathing, or with breathing, sneezing.
What, the reticular formation? Show me where it says that.
I don't
This
know, that's
is
what I
medulla.
read on notes.
Oh, all right. No. I
Yeah,
don't think
okay,
it,
right here. At the same time, the RF controls reflexes involved in breathing, sneezing, coughing, and vomiting.
at the same time, but that doesn't mean, it's more the medulla function. The reticular formation influences attention. Okay. Coughing and vomiting, swallowing, heart rate, breathing, it's more, right? It's a medulla function. Let me tell you what the reticular formation, what I'd like you to know about it. One of the most important things the reticular formation does is it maintains consciousness or attention. That's one of the most important things that it does. So, damage to the reticular formation could result in what?
Coma.
Coma. Which is why a blow to the back of the head can be so dangerous. A damaged reticular formation can result in coma. Now, there can be many reasons for coma. Right? Many. In this particular instance, there is insufficient internal stimulation to wake up the upper brain. See, the reticular formation stimulates the upper brain, right? Wakes it up. If the reticular formation is damaged in some way, then there's insufficient internal stimulation to wake up the upper brain. Now, coma is different than brain death. Yes? It's not brain death. Brain death happens when you're no longer receiving electrical signals from the upper brain. So when you look at the upper brain, you get like a flat line. All right? A flat line like this. Which means there's no more electrical activity, brain is dead. With coma, you don't get this. With coma, you get electrical activity, but it's low-level electrical activity. So we know that the upper brain is not dead, has not died. Okay. But again, there can be many reasons for a coma. This happens primarily because of a lack of internal stimulation to wake up the upper brain. That's one of the most important things the reticular formation does. And one other part of the brainstem, it's identified in the text, it's not identified in this picture, but it's the pons. This is the pons right here. That's the pons. Now, what does the pons do? Anyone remember? Plays a role in the sleep-wake cycle. Plays a role in the sleep-wake cycle. Okay, that's what the pons does. And in addition to helping, right, to aiding in the transmission of information. And it transmits information coming in from the spinal cord, right, to the upper brain. But those are the things I would like you to know about, a little bit about the brain stem. Okay? And actually, I mean, when it comes to sleeping and waking, right, the medulla plays a role, even the reticular formation plays a role, but the pons plays the largest role. Right? But the other parts of the brain stem play a role.
You said it was the area in blue? Is that what you said?
No, this is the reticular formation right here. This
Oh, the
structure.
pons. Yeah, where's the pons?
This is the pons right here. That.
And the lower lumpy thing is the medulla?
This is the medulla. Okay. That's the medulla. That's the pons. Pons is not identified. It's not identified in this picture, and it's not identified in your book. It's mentioned in the text. Right? And it's part of the brain stem. I don't know why they don't identify it. Then going above, right, just looking beyond, before we look beyond, this structure back here is the cerebellum. This is the cerebellum. In this model, this is the cerebellum. this little mass at the base of the head. Right? Remember that the cerebellum wraps around the brainstem. So this is your cerebellum. What's the cerebellum do?
It regulates coordination and movement.
Coordination, movement, posture. So, how is it that you know how to ride a bike, climb a ladder, swim? That's not verbal information. That particular information about movement and about the body, that's stored in your cerebellum. That's the kind of stuff that the cerebellum does. What actually happens is a command comes down from the higher brain, from the upper brain. So you get on a bicycle and you start to ride, right? The command comes from the upper brain, but the specific information about riding a bike is contained here in the cerebellum. You jump in the water, you begin to swim. Right? So the information, the specific knowledge about the use of the body to swim, right, or to do something else is contained within the cerebellum. And these two structures, brainstem and cerebellum, as far as we can determine, these are very old structures in the brain. Old, meaning that they've been with hominids for a long time, as far as we can tell. Now, how do we know that? We don't have any brains hanging around from 50,000 years ago, but we do have some fossilized skulls, right? And when we look, right, and when we look at the skull, right, the brain is gone, but the brain leaves an impression on the interior of the skull. And so you can look at the impression that the brain leaves. Leaves an impression on the interior of the skull, but here, right, for something like the brainstem and the cerebellum, you can just look at the cavity. Here's the opening for the brainstem, right, where the spinal cord comes up. Here's the cavity for the cerebellum, right? All we have to do is look and measure, and that makes sense because we're talking about things that relate to the body, right? Vital functions in the body, movement. Those are not the things that would have been likely to change, you know, as humans move forward, as humans progress. Right? The changes would involve the upper brain, right? Not necessarily the brainstem and the cerebellum. Looking just above that region, this area in here, is known as the limbic system. And in this model, the limbic system, we said, is sort of centrally located in the head. And it's right here. This is the limbic system. This is the limbic system, right? This region right here, sort of in the center of the brain. Now, if the brainstem controls vital functions, what is the limbic system?
Emotional response.
Yes, plays a role in emotional response. That's what it does. Okay, parts of the limbic system. Okay, here are some parts of the limbic system, many of which we'll talk about. That is your limbic system. So, one part of the limbic system is the thalamus. There's the thalamus. Tell me what the thalamus does. Yes. It relays information to the cortex, coming in from the senses. So information that comes in from the senses stops in the thalamus. And then the thalamus will direct it to the appropriate brain region. So it goes out from there. How about the hypothalamus? Here's the hypothalamus. Now the hypothalamus is about the size of a dried green pea. It's small, but it's extremely important. Yes? Yes. It deals with what? It deals with emotional responses, right? A range of emotional responses. Right? Rage, terror, pleasure, right? A range of emotional reactions. Anything else? Motives. Now the textbook calls them motives. What do they mean by motives? Like what?
Hormone release.
Huh?
Hormone release.
Hormone release, regulating things like,
Body temperature.
that's the internal body environment. The motives, right? Motives, what they mean by motives, most psychologists call them drives. Things like hunger, thirst, sex, hypothalamus plays a role in the regulation of those activities. And it also plays a role, you said body temperature, in managing the internal body environment. Things like heart rate. This is where we more often see heart rate, is from the hypothalamus. Heartbeat tends to be more medulla. Heart rate tends to be more hypothalamus. Right? Heart rate, temperature, blood pressure. That's your hypothalamus. Hypothalamus, we'll mention the hypothalamus again, but at one time in the United States, when people wanted to lose weight, what happened? Physicians used to prescribe amphetamines. You can't do that anymore. Right, I'll probably mention this again because there's some other stuff in the chapter I'll show you on Monday. Why amphetamines? Well, actually, amphetamines in touching various parts of the brain would actually touch the hypothalamus. And in touching the hypothalamus, what they did was they shut off hunger. They shut it off. It shut it down. Right? Shut it down. It's not a good way to lose weight at all. Right? In addition to the problems with amphetamine use and abuse. Right? So you can't do that anymore. Right? Not a good way to lose weight because it's only weight loss that's controlled by drugs. Once people start taking the drug, there's no lasting effect. Right? All the weight comes back. Right? You haven't done anything with the person. It was a change that was brought on only by chemical manipulation. It was not a change in the individual. Somebody asked me about. Did somebody ask me about that in one of my classes? Did you ask me about that? That's where the hypothalamus. That's where hunger is controlled by the hypothalamus primarily. But even though hunger is controlled by the hypothalamus, when people eat, what people eat, how much they eat, is a function of many other things, and not hypothalamus. Not hypothalamus. Just hunger is controlled by the hypothalamus. How about the hippocampus? Yeah?
Storing memory.
Okay. Hippocampus plays a role in long-term memory. The conversion of something from short-term to long-term, your ability to hold on to something, to retain something, is a hippocampus function. Now, is the hippocampus the place where memories are stored? Or is it just part of a process?
Further form.
Huh?
Further form.
Yeah, it's the process, right? The formation, right? It's the process of memory storage, right? It doesn't deal with the storage per se. So, where do memories go? Well, that's a good question. Right? Beginning in the 1940s, there were a group of researchers who were trying to understand memory. And believe me, there's a whole lot of questions that we still have about memory. There's a whole lot of things about memory that we just don't know. So what these researchers did, right, to try and better understand memory problems is they wanted to know where memories were stored in the brain. Where do memories go? So they take a group of rats. They take these rats and they train the rats to run through a maze. So the rats learn the maze. Now you use rats in psychological experiments for lots of reasons. They're small, you keep them in a lab, but the brain of the rat, right, is similar to the brain of the human. In that you got a brain stem, you got a cerebellum, you got a limbic region, and you got a cerebral region. All the same structures. So they take these rats and they train these rats to run through a maze. So the rat learns to run through a maze. Then they take the rat out of the maze and they remove a small piece of the cortex. Then they put the rat back in the maze. The rat still retains the memory. They take the rat out of the maze again. They remove another piece of the cortex. Put the rat back in the maze. And they keep doing this. Now it gets to the point where they removed so much of the poor rat's brain that, a rat's like stumbling around in there. So they got to start with new rats. So they know we removed this. Okay, now we got to start. This research, which began in the 1940s, went on for more than 20 years, being conducted by different groups of researchers through the 1960s, until the late 60s, actually. And it didn't matter. No matter what part of the cortex was removed, the rat always retained the memory of how to get through the maze. So where is memory? See, in the 40s, the belief was that it was going to be in one specific location. Right? After 20 years of research, right, that specific location never appeared. So by the late 60s, 70s, the thinking then changed. That rather than looking for one specific location in the brain, there's a lot of material, especially memory, that spreads all over the brain, that goes all over the place. And that's what the research said. Now, brain researchers in the late 60s, 70s, and 80s started to compare and talk about the brain in a different way. You know what a hologram is? You have it on your credit cards. You tip the credit card, you see a three-dimensional image. Well, you could take a picture. Let's say we take a picture of the outdoors, right? And we put it on a holographic plate. So here's this glass plate. And I bring this glass plate in. If we put it in front of the room, when you look at the glass, right, when you look at the picture, what you would see is you would see what appears to be a three-dimensional image, right, as if you were looking at a 3D movie, as if the trees and the sidewalk and everything would appear to come out at you. Now, if we have this glass plate, if I take this glass plate and I break it, I break the glass, and I pick up any piece of the glass. So I pick up a small piece of the glass and I look through it. What do I see?
Part of the picture.
Huh?
Part of the picture, and it's still in it.
Picture is still there,
Yeah. You're still gonna see
but the
part
whole picture is there
in that one little piece.
in that one little piece. No matter which part I pick up and look through, I can see the entire picture. Now, the picture is not as sharp or as clear. It's interesting because the whole exists in the part. Right? And brain researchers, most especially by the 90s, were using this analogy to explain how much of the brain worked, especially with things like memory. Right? That there's a whole lot of functions that are not located in just one region, but rather are diffuse, that spread all over the place. They are not just in one part of the brain. Yes?
If memory is in multiple places in the brain, say someone was in an accident, people lose memories. Like, they can't remember what happened maybe 5 years ago because of that accident. How does that happen if memory is all over the brain? Maybe that one piece of the brain dies,
Yeah.
but
Yeah, one piece of the brain can die. I mean, I can't answer that question. I mean, memories, from what we know about memory, things spread around the brain, but brain damage can remove a particular memory, or brain damage can destroy an individual's ability to speak. You know, I can't explain. I don't know the answer to that. There's a whole lot of stuff about memory we do not know. You ever been with somebody who's got a memory problem? They usually have an inability to remember what happened 5 minutes ago. They can remember what happened 20 years ago, but they can't remember what happened 5 minutes ago. Why is that the case? Well, the old memories are stored in the brain. Right? And they were stored when the hippocampus was working properly. With memory problems, when people have memory problems, one of the things that recent research has identified is that the hippocampus diminishes in size, it shrinks. It diminishes in size, doesn't work anymore. So you go see somebody in the hospital, maybe it's your grandmother or your grandfather, and your grandmother doesn't remember that you called her this morning and told her you were coming. Right? She's eating lunch with you, and she's telling you the same story that she's told you, last week, last month, right, 6 months ago, same set of stories, right, over and over. And while you're there with her for an hour, she'll probably tell you the same story more than once in that hour, right? Because she doesn't remember, she can't retain anything. And the reason she can't retain anything is because the hippocampus doesn't work anymore. So there's no ability to retain. I mean, even for like a moment, it's like incredible with people who have memory problems, you know. But the old memories can still be in there and still floating around. So she can retain them, but she doesn't remember that she told you them yesterday and last week and last month and 6 months ago. Yes?
so with Alzheimer's, is it the hippocampus shutting down or something?
Well, the hippocampus is involved in Alzheimer's. Alzheimer's is one form of dementia. There are many forms of dementia. See, what happens with Alzheimer's is that eventually the person will lose all the old memories to everything. They can forget how to eat. They can forget, right, lots of things, because the disorder starts ravaging the entire brain, and it seems to emanate from around this hippocampus region, right? Here's the limbic system. These two little structures in here that you see, this is the hippocampus. The hippocampus is on both sides. It's on the left side and it's on the right side. And Alzheimer's seems to emanate from this region out. You know, the brain starts producing a protein structure that just starts ravaging the brain, just starts destroying it, like a Pac-Man. It just starts eating away. If you have to leave, you can leave, okay? All right? It just starts eating away at the brain, just starts ravaging the brain, right? Why the brain produces that protein, why some individuals, not others, we don't have the answers for that. And the best we could hope for is that we might be able to slow it down. We can't stop it, we can't reverse it. And there's even controversy about whether we actually slow it down or not with the pharmaceuticals that are on the market. You know. But Alzheimer's is just one form of dementia. Right? But what happens with memory problems is that the hippocampus changes. So if it's not Alzheimer's, some of the old memories will stay in place. The person will just continue to tell you things over and over and over again. With Alzheimer's, they'll lose the old memories too. And, you know, brain damage in one region can knock out memories or can knock out something? Can other parts of the brain, we'll talk a little bit more about this next week. How flexible, how plastic is the brain? This is something we'll talk about next week. And then we've got the amygdala. Tell me about the amygdala. Fear responses. So, at a point when you are extremely frightened, right, or panicked over something, the amygdala is activated, but it's intense. It's got to be an intense fear reaction. Now, when the amygdala is activated, the amygdala can bypass all of the other brain circuits in order to move material to the upper brain. So it doesn't have to go through normal channels. How many of you remember where you are on September 11th of '01? Be a memory you have forever. Look at where the amygdala is. Here's the amygdala, here's the hippocampus. And there's probably, right, some evolutionary significance to that. Because our ancestors, right, since predators were much larger than our ancestors were, right, they had to retain information, right, about frightening situations, about things that put them in danger. Right? And so we still have it. Right? But here's your amygdala, here's your hippocampus. Any sort of startle response will activate, right? But it's got to be extreme. It's got to be something that's very extreme.
Oh,
Yes?
is anxiety associated with that?
It can be. Anxiety can be associated with the amygdala, and it can be associated with the hippocampus. There's research right now that's looking at that, even post-traumatic stress. Yes, somebody else raised their hand. Yes.
What does it trigger?
What do you mean, what does it?
Like you said that it's associated with fear, but what does it do with the fear?
It activates parts of the brain. Okay? It alerts the brain that you're in danger. Okay? And it's going to be something that happens very rapidly.
So would that be, like it would, I would assume that would be the thing that kind of juices up your adrenaline release?
Fight or flight?
Fight or flight, it's involved in fight and flight, but actually other mechanisms are involved in fight or flight. The hippocampus, the hypothalamus plays a role, a very big role in fight or flight, because it's your autonomic nervous system. So there's a whole series of mechanisms that get involved in the fight or flight reaction. So it's your hypothalamus, it is part of your amygdala, but it's a far-reaching response that goes throughout the brain. See, the amygdala, what the amygdala is going to do is it's going to activate your cerebral area. It's going to send blood, right, up to the upper brain. That's what it's going to do. That's why when people are nervous, right, lots of times when people are upset, they have stomach problems. Because the reason being that your body, in sending blood to where it needs to go, will stop digestion immediately, because it's not important to digest food now, which is why a lot of people who find lots of situations upsetting in life frequently have either digestive issues or stomach problems or colitis, or these are things that they get disrupted. That region of the body gets disrupted because of other things that are going on in the brain. It's not just one mechanism. Right? Remember, the brain is like an integrated system. A whole series of parts work together in unison with one another. Yes?
I don't know if we're eventually going to talk about this, but like, how does, like when you have like an eating disorder, how does the brain like work where if you do it enough times, like you have to every time you finish eating, while like, I don't understand how the brain,
Eating disorders are caused by a person's psychology, not by the brain per se.
well, the thing that like confuses me is that like after they eat, they feel like they can't keep it down, or they have to puke it up, but it just doesn't make sense that like it actually like there's like no possible way they can keep it down. Like, how does that work?
You'll see when we look at some other.
Talk about it.
Yeah,
It's just, it was weird.
You know.
thinking that you can't not keep it in. You have to. It's like your brain triggers, like, or whatever your.
Well, it's a learned response, you know, it's a learned response, and people who have eating disorders, it's not a brain malfunction per se. It has to do with other things going on in the person's life. It's not a brain malfunction. It's not the brain telling you not to eat. It's you telling you not to eat. People who have eating disorders are hungry and think about food a lot, but they just refuse to eat. So that's not, it's not a brain problem per se. It's an experiential problem. A problem that the person has with himself or herself, mostly hers. Right? Most people who have things like anorexia and bulimia are females. The vast majority of them. But we'll deal with that just a little bit in some other things that we look at later on.
The eating disorder, though, we never feel full. I don't remember the name of the disorder. No?
Isn't that though related to the thing, the pico or whatever, where people eat bizarre things? Isn't that related to that or no?
Not to my knowledge. No. Pico is where people eat like inanimate, stones
Right,
and
like metal or
nails
whatever,
and.
right. But I thought that was related to that.
Could be. If it is, I'm not aware of it. Right, so that's a little bit about your limbic system. We're going to look at some other stuff in the limbic system. Now moving, right, when we look beyond the limbic region of the brain, and we look at the upper part of the brain, this is the cerebrum, or the cortical region of the brain. Right, the cerebral cortex or the cerebrum. This upper part of the brain, that's our higher order functioning center. This is the thing that is distinctly human. It separates us from other mammals. Okay. Did you have a question? Okay. This is a higher order functioning center. And when we talk about the brain operates as an integrated system. That means that different parts communicate with one another, right, to make us who we are and are involved in the complex actions that we engage in. Now, even though the brain operates as an integrated system, there is still some degree of specialization that exists within the brain. One way to talk about some of that specialization within the cerebral structure is to look at the lobes. There are 4 lobes in the cortex. 4. And they're identified here. You have them in your book. The occipital lobes. Back part of the head. Okay, this region back here. What's that involved with? Vision. Reception and analysis of visual information. Damage to this area of the brain could result in partial or total blindness, even if there's nothing wrong with the eye. Right? The eyes might be fine, but if this part of the brain is damaged, people can't see, or they have partial sight, because there's nowhere for the sensory information to go. Yes?
What about a hard enough hit to the head that causes you to be dizzy periodically from time to time? What would that be caused by? Like,
That causes you to be dizzy. It could be caused by any number of things, But a blow to the head will result in the brain banging around on the inside of the skull, which is what a concussion is. The brain swells up. Right? It swells up. The temporal lobes are on the sides of the head. They're on the sides. What do the temporal lobes do? What's one of their primary functions? Hearing, right? They seem to be involved in some other things as well. We're going to talk about it mostly next week on Monday. But the temporal lobes play a role in hearing, and you'll see some other stuff about the temporal lobes. How about the parietal lobe, or lobes? sensations. Bodily sensations, tactile sensations, things on the skin, things on the body, sensation. That's the parietal lobes. And then the frontal lobes. Now the frontal lobes, this is an area just behind the forehead. Right? This region right here. This is the frontal region of the brain. What about the frontal region? Yes.
They play a role in your sense of self.
Your sense of self, and what else did you say?
I just said play a role in your sense of self.
Your movement?
Movement. Yes?
Ability.
Huh?
Like ability to do things.
It does involve ability to
It's higher mental ability.
higher mental abilities. Higher mental abilities. Now, when we talk about the cerebrum, when we talk about this structure in the brain, right here, we are talking about a really sophisticated brain area. The entire structure of the cerebrum. Higher order function. Higher order function. When we talk about the frontal lobe region of the brain, the frontal lobes are particularly sophisticated. Complex thinking, abstract thinking, your ability for foresight, planning, insight, all of that seems to be a frontal lobe function, specialty. It is a really sophisticated part of the cerebral structure, very sophisticated. So tell me what a lobotomy was. Yes?
People with mental disorders, they cut out the frontal lobe of the brain so they give them control.
It did involve a surgical procedure. Right? They didn't specifically remove the frontal lobes.
They just squashed it around.
They just severed it from the remainder of the brain. Now, they did it. Why'd they do it?
To the people with mental disorders, they'd have control over them. They wouldn't really have. They'd be bland people. They wouldn't have any emotions.
Yeah, they wouldn't have anything.
Don't they mainly do it to people who are actually considered dangerous in some way?
That was what was supposed to happen. Okay? You see, the powerful sedative drugs that we now have available to us, they didn't exist in the 20s, 30s, the 40s, even most of the 50s. They weren't around. Powerful sedative drugs, major tranquilizing drugs, antidepressant drugs, the drugs that we now know today started to become available in the mid to late 50s. They didn't get into use until the 60s and 70s. So prior to that time, what do you do with someone who's incorrigible? We didn't have the drug treatments that we now have.
Restrain them.
They were restrained, right? They had to be. The thinking was, at that time, in the 20s, that the frontal lobe region of the brain had something to do with the incorrigibility. So, right, it was believed that if the frontal lobe region of the brain has something to do with this, what if we could cut off the impulses from the frontal region of the brain to the rest of the brain? And that's what a lobotomy was. In the old days, what happened with lobotomies were they would shave the head, drill a hole through the top of the skull, and insert an instrument that looked like an ice pick. They would insert this down, and then they would just move it, like this. Now, in the United States, right, it's hard to determine how many people were lobotomized, but thousands and thousands of people got lobotomies. Right? Somebody actually tried to conduct research on this about 15 years ago. And when you start looking at things like hospital records from the 20s, 30s, and 40s, state hospitals, I mean, and some people who are lobotomized are still alive because lobotomies were being done in the 60s, 70s, some were done in the 80s. They're not done anymore now, at least not in this country, at least not legally. They're not done anymore, right?